So we're going to talk about AI frameworks on Aurora and Sunspot today. So at anyone who was in the Insight Hackathon last week, some of these slides will look a little familiar. Some of the overview is very similar, but this talk is targeted very much towards Aurora. And I'm sorry if you have to, sit through some of the same content for a couple slides. At ALCF, on our big supercomputers, machine learning frameworks are one of our key application drivers. So we support them on our systems in the data science and AI ML group. Particularly, we focus on a couple frameworks, TensorFlow, including Horovod, Pytorch, and JAX. These are the big three that we're looking at. And if you have other frameworks that you're interested in running, they're not currently supported by us, you're welcome to open a support ticket and reach out and talk about it with us to see what we can do to move forward. Inside of ALCF, what we do for these frameworks is we focus on optimized installations. So on Polaris, that looks like building everything with CUDA. On Aurora and Sunspot, that's building everything against the Intel stack or working closely with Intel on their installations. We do a lot of performance tuning measurements so that we can come to you with the optimal settings to tune your application for these systems. And we also take a look at scale out best practices, particularly as you hit the extreme scale limits on some of these supercomputers. The things you have to do to optimize scale out may change. And we hit interesting problems at the largest scale. So we try to solve a lot of those things for you. So we can come to you in sessions like these and tell you how you might take your application and scale it out to the largest scales. For Aurora in particular, all of this is a really close collaboration with Intel. And we balance our user needs with their optimization strategies. So for several years now, we've been helping them prioritize what needs to make it onto Aurora in time for users, what is less critical, even though it may be on their roadmap for Aurora. So the software you'll see on Aurora has been born out of that collaboration. On Aurora, as all of you probably know if you're in this talk, it is not CUDA supported. So Aurora's compute nodes have Intel's Data Center Max 1550 GPUs, also known as the Ponte Vecchio GPUs. Despite the lack of CUDA, the AI frameworks you are already using are already well supported on both Sunspot and Aurora. So things look slightly different, but you should expect good performance. In this talk, I'm going to go through the basics of using these softwares on the Intel GPU systems. And as well, I'll go through some examples of AI codes on our Sunspot and Aurora systems. I will put some extra emphasis on the things you need to change in your code to convert from CUDA-based codes to Intel-based codes. I don't think you'll be overwhelmed by the number of changes you have to make. Much of it is pretty straightforward and relatively simple. Okay, so one of the things that is sort of the most obvious entry point on Sunspot and will be on Aurora is a difference from a system like Polaris is built-in frameworks to the node compute image. And I can get into some of the details here if everybody wants to, but at the end of the day, when we were testing on Aurora earlier this year, before it was limited access for HPL runs, we noticed that at the largest scales, launching of Python codes, which is what almost all the AI applications are, has severe limitations in startup time that we trace to file system issues. So you can see in this graph the time it takes, between the MPI exec and the first iteration of an application really starts to grow as you increase the number of ranks. And at about 128 to 256 nodes, this starts to be really detrimental. And this only went up to a few hundred nodes. You can imagine this exponential curve getting worse and worse as you go bigger. So there's a lot of details that we put into debugging this, but at the end of the day, what you need to know is that when you go onto an Aurora compute node, the framework's components are part of the node image, and you don't actually have to hit the file system to load the frameworks. Okay, so let's talk about Sunspot. Sunspot is currently set up to mirror Aurora as close as possible. Things will look a little bit different when Aurora comes back on, but the basic principles will be the same. So if you go on to Sunspot and you do module avail frameworks, you will see right away there is this opt Aurora path where there are module files, and one of them is frameworks 2023.12.15.001. In Intel language, this corresponds to the 2024.0 frameworks drop. We got it 2 weeks before the end of 2023. You can load it right like this, module load frameworks 2023.12.15.01. And when you do which Python, it will point to this one. And you can scroll over and see you've got a Python that's from opt. And that doesn't hit the file system. Okay, under the hood, Intel's optimizations for AI frameworks are not built on CUDA, as we've talked about. Their ecosystem is referred to by Intel as one API and includes a lot of libraries that share similar functionality with the CUDA equivalent. So just to kind of help you map this, one MKL on Intel corresponds to CUDA's math library, and MKL stands for math kernel library. One DNN and cuDNN have some equivalents. One CCL and Nickel, which is the NVIDIA Collective Communications Library, are similar. Python, at the Python level, on NVIDIA, you can use something like CuPy. On PVC, you can use this package called dpcontrol, which will help you map Python operations into streams and GPU coordination. And there's things like DAL and DAL for Pi, which is data analytics library. And that corresponds to something more like Rapids on the NVIDIA side. And these aren't meant to be an API compatibility layer. These are just similar libraries that serve similar functions. Most of them are well integrated into the frameworks, and you'll likely never get down into the details of a one DNN versus a cuDNN call. Okay, for optimized performance on Aurora, most of the packages that you'll use require extensions. So what this might mean is you have to do some sort of pip install or Python import for extensions. But if once the slides are posted, hopefully they are already, you can click these links to learn more about these packages. So for example, Intel extension for scikit-learn is the classical machine learning techniques extension. There is Intel extension for TensorFlow, which enables XPU support in TensorFlow. We've got Intel extension for Pytorch, and that's bringing torch.xpu, which replaces torch.cuda in your code. There's also extensions for DeepSpeed, OpenXLA, Triton, Transformers, Horovod. You can click all of these links to find out more in the slides. Okay, one thing you may have noticed already is I was talking about the frameworks drop that we have on Sunspot, and it was the 2024.0 release, but if you're up to date with Intel's frameworks deployment, they are on their 2024.1 release. We don't want to block users from using the latest and greatest code, but it also takes time for validation and deployment of a drop into an image. So the frameworks drop on the compute node image is necessarily delayed compared to the Intel latest drop. What this means is we have a preview area, which is in soft. So you can do module use soft preview module files. And then there's a path here that you can copy if you like. And then when you do module avail frameworks, you will find two new frameworks. So frameworks 2024.04.15.01 and 04.15.02. This is a minor update with some package upgrades from the 2024.1 frameworks, but both of these are built on the same one API release. So you're welcome to use this on Sunspot, and at the scale that you'll run on Sunspot, you shouldn't hit any issues off of you doing module load from soft area. Okay, so sorry, this slide is not super well formatted. I don't know what happened here, but if you want to use soft at scale on Aurora, it's not going to be simple, at least not at first. So if your code can use the version deployed into the operating system on the compute nodes, use that. And if you want to test the next drop and you're doing small scales, so 128 nodes or less, which by the way is actually about as much compute power as Polaris, you can just use things right off soft and it should be okay. But if you want to go to the latest and greatest at scale, or you need packages that aren't installed, you may need to use what we're kind of calling the tarball ramdisk method. Okay, so each node on Aurora, if you're not familiar, has a local temp area that's based on RAM. So what we've done in the past, and we will likely continue to do for the foreseeable future until soft is stabilized, is we'll provide tarballs of one API in the Python ecosystem installed into the temp area that can then be deployed into temp on each compute node. So what that looks like is temp is RAM disk. You can rsync a tarball to temp, and it does decrease the available CPU memory by a little bit, but it has a significantly better latency and scalability from soft. And you can also deploy a virtual env to this space for additional packages. So if you need some custom Python package or code and you want to run it 10,000 nodes on Aurora, this is likely what you'll need to do. You can also put a virtual env into the Lustre space or the home space. And there does appear to be some special quirk of soft that makes that area particularly worse. So if you want to avoid the RAM disk wrangling, you're welcome to try things off of Lustre. And Deos is also a possible path on Aurora eventually. But if that's not scalable for you, the RAM disk appears to be the most scalable method. And at the largest scales, for the users who are really looking to run on something like 50% or more of Aurora, this is probably going to be the method for most of the lifetime of Aurora, is my guess. Okay, so inside the Python packages that we've installed with Intel, you can take a look at what's in that Python package. So, for example, once you've set up the modules, you can do pip list and then grep for Torch. And you'll see a couple packages here. So there's Torch itself and Torch Vision, and then there's this Intel extension for Pytorch, which is also needed. And unless you have a compelling reason to, it's really recommended that you use this module if your Python's applications Python needs are supported here. And if they're not, you should extend it with virtual env. And if there's anything else that you need help with, of course, reach out to us at the support email list. So if you want more packages, here's a sort of a simple way to do it. So for example, you can use a virtual env this way. The first thing you do is set an environment variable and point it at temp. So for example, temp/conda extension, you could name it after your package, whatever. Make sure the first path is temp. Do this just one time. Sorry, that's a leftover comment from the previous week's slides. But you set up your Python virtual environment with this -- system site packages flag, which will make it use the Python from the conda environment, and it will build a folder in the temp area that will include your Python extensions. You set it up like this after you do conda activate, if necessary, and then you can install what you need into your virtual env. So pip install Pytorch Lightning, for example. And then when you're all done, create an archive of your virtual env once you've installed everything. So there's a command you can run that will make a tarball called virtualenv.tar.gz. You can name it whatever you want and store it in Lustre, and that's fine too. When you want to go run this in an actual job application, so this would go into your qsub script, you do something like this step on lines 4 and 5. So once you know how many nodes there are, you can untar the package to temp once per job. So I'm running MPI with one process per node for however many nodes there are. And I'm just doing that on that tar step to extract it into temp. Then you do, you set your virtual env directory name, and you can source this line here, 7 to 8, to activate it again once the frameworks are installed. Okay. That's kind of a complicated set of instructions to really scale out. And I hope it's better in the future, but if you're really pushing the limits on Aurora, I hope this is useful. All right, one thing I like to cover in these talks about the AI frameworks is people sometimes have questions about which frameworks to use. I'll talk a little bit about things on Aurora specifically with these frameworks. So a lot of newer models are using Pytorch and JAX, but if you're using TensorFlow, On Aurora, mixed precision gets the best performance, or bfloat 16 mixed precision in particular. TF.function is enabled on Aurora, and op fusion has worked in TensorFlow to get good performance. Graph compilation is something that's coming, so that's an enablement path that Intel is working on. So things like XLA compilers here work on Polaris. They're experimental on Aurora and Sunspot, and you may actually see degraded performance at the moment by enabling XLA, but that's still a work in progress from Intel. Okay. On Aurora, Horovod has been our scaling method of choice for TensorFlow. The documentation for Horovod is pretty good, though it's unclear with TF 2.16 what the future of Horovod is and if support is going to continue. One optimization that's particularly useful for Horovod at scale is to set the number of groups argument in Horovod to 1. And this is an optimization that Intel has pushed us towards because of some concurrency complications with their compute and communication overlap. And this will buffer all of your communication into one all reduce for optimal performance. Particularly if your model is very, very big, this may be a bit of a bottleneck, but we'll see when users get on and run what they experience. And if you're using TensorFlow and Horovod and you're planning to continue this long term, we'd be happy to know about your use case and the issues you have scaling up TensorFlow on Aurora. In terms of TensorFlow adaptations to XPU, it's actually pretty simple. So it's one of the easiest frameworks to port. I believe the TensorFlow extension will import automatically when you load TensorFlow. Most of the changes just kind of look like this. You can do tf.config.list physical devices XPU instead of GPU. And then you might set your visible devices to just your local ranks, for example. And you can click this link from Cosmic Tagger here below, and it will take you to this portion of the code. That's an ALCF application that is available in all the frameworks. In terms of Pytorch, it's definitely the most common framework we see on both Polaris and Aurora. It's more NumPy-like, and I said this last week as well, but I think many of us are switching to the phrase Pytorch-like, which tells you how ubiquitous it is. Graph compilation is available in Pytorch, and you should try to use it if you can in the framework's 2024.1 drop. So not the one in the compute node image, but in the one in preview module files. Torch.compile should be functional. However, much like XLA, it is a work in progress for performance. So Intel is still ramping up Torch.compile. You should try it, see how it goes, and you should continue trying it over the next 6 months to a year to see how performance improves. Yeah, you can see it here in the frameworks drop that in particular it's available, and decreased performance in some models is expected. So if you see your model run slower at this time, just turn off Torch.compile. As I said last week in the hackathon talk too, the Pytorch ecosystem is really broad. And we at ALCF and Intel have not installed every package under the sun. So the virtual env environment is particularly important for Pytorch. And if you can't get what you need going, always reach out to us for help. Okay, Torch is a little bit more complex to adapt to XPU. So the first thing you do in your Pytorch code is you typically have to do this call. I put it in a try except so that I can run this on Polaris as well, and it doesn't find the Intel extension for Pytorch. And then it just continues. But when you import this module, import Intel extension for Pytorch, it will make available calls like torch.xpu instead of torch.cuda. So things like this will now work once you've done that import. You can call ipex.xpu.device, or you can even just say torch.device and point it to XPU with a number. Pytorch on Polaris typically uses the channels first format for optimal performance. On Intel's devices, it is not that way. So you can use channels first for okay performance, or you have to use channels last for improved performance. What that means is in your code, you'll probably do something like this for your model. So your network will get move to the XPU device, and then you can call to with memory format equals torch.channels last. You just have to do this once for your model. And then for all of your inputs and labels, you likely do it the same as well. So you do this with every batch. So you call mini batch data, image is .to memory format, torch.channels last. Pytorch can also be scaled with Horovod or via the built-in DDP method, and both are supported on Aurora and Sunspot. We've seen a little bit better performance with Horovod on Pytorch due to some of the concurrency issues as well. And use Horovod num groups equals 1 as well. If you want to use DDP, which many people do, DDP's backend on Aurora is the CCL backend. So instead of nickel, you would say CCL. Don't use glue or MPI. CCL is the best one. Before you can call a init, you have to import this extra package, import 1CCL bindings for Pytorch. And that will make CCL work when you do torch.distributed.initialize. Deep speed is also available in an early drop on Aurora and Sunspot. And I myself am not a deep expert on deep speed, but I reached out to our local experts for some comments here. So if you want to use deep speed, here's some of the things it can do for you on Aurora. So you can use the zero offloading scheme to save memory by partitioning both your optimizer state gradients and even your model weights across a big run. Pipeline parallelism, I believe, is a work in progress on Aurora for use cases that don't fit on a single device. Other things are trickling into other areas. So Pytorch's fully sharded data parallel is inspired by deep speed. Megatron has a lot of optimizations from deep speed, though I'll point out that Megatron is an NVIDIA product, I believe, and I don't expect it to work on Aurora. And then Intel, of course, has Intel's extension for deep speed, which is essential for good performance. And deep speed on the XPU platform is still in development. If there are features or performance improvements that would really benefit you, please reach out to us because we have ongoing conversations with Intel about what to prioritize and when. Pytorch Lightning also is available on XPU. It's not officially supported by the Pytorch Lightning team, but there is an ALCF branch of Pytorch Lightning that works. So you can click this link to find the repository and install it from this version instead of via pip. You have to select the XPU accelerator option. So what that looks like is, in this line of code here, you would say accelerator equals XPU accelerator. And if you get an error that, XPU accelerator can't be imported from Lightning Fabric accelerators, you've probably got the mainstream version of Lightning installed. Unfortunately, Intel has not yet merged their version, so ALCF's branch appears to be the most functional at this time. So once you've got our branch of Lightning, scaling it is pretty easy. You just use the MPI environment to launch with MPI exec, and you can use a deep speed strategy the same as you would on Polaris, where you pass in the cluster environment as the MPI environment, and you just pass that strategy to your trainer, and things should work. Okay, JAX on Aurora. So if anyone's not familiar, JAX is the successor to Autograd, as well as built with XLA as a backend for NumPy. JAX implements NumPy's interface even on the GPU. So on something like an A100, you get a really great GPU performance out of the box. And it has a performant backend for nearly every operation in NumPy, as well as SciPy. It's also purely functional, so your coding style changes a little bit. And your Python performance issues, if you have any, can be really reduced with the JIT compilation. And it also has one of the best autograd systems of all of the auto differentiation packages out there, and the best documented one. So you can compose their autograd with their other functional transformations, and you can get, neck deep in the vector calculus and differentiable calculus that you have to know for the autograd understanding if you follow this link here to their autodiff cookbook. On Aurora, JAX has early support. So it's not yet deployed on Aurora at the same level as Sunspot, since Aurora is not yet open to users again. And all of the JAX modules that we have built and installed are done by LCF staff, me in particular. So it's still very early development for XPU. I would say that most operations in JAX are functional, but performance can sometimes be subpar. MPI for JAX is supported, but you can't use jax.devicePut at this time. There's a bug in JAX. It's already been fixed, but it hasn't made it to the XPU port yet, so expect that probably in the next few months. The code at the bottom of the slide is from Sunspot. You can log on today and see what's available from JAX. If you have to pick one of these, just take the latest 0.4.25 drop from JAX. Okay, so scaling out JAX on Sunspot, you can do several methods. PMAP and PJIT, which is just regular JIT with extra args, they're parallelization routines to parallelize your functions in JAX. Everything is done for you, but you have to know what changes they'll make to make it work properly. MPI for JAX is definitely the simplest scale-out method. So you can do jittable MPI collectives within JAX. It's supported, this should say Sunspot. You just can't do the device put paradigm yet. There's also JAX's newer shard map technique. It's definitely more complicated. It has a lot more fine granularity and it was a little bit harder to use, to be honest. For those of us used to doing MPI collectives, a shard map is a very different way of thinking about parallel computation. As far as I know, shard map is largely untested on Sunspot. So if you go in and test it, please send reports if things don't work the way you want. And like I've said, all of these are still in the experimental stage on XPU. So bug reports are welcome and encouraged, and we can take those back to Intel and get fixes in the pipeline. Okay, so this should say best practices for running on Sunspot. Sorry about that. So I'm going to use Cosmic Tagger, like I did last week, as an example that ALCF has built to demonstrate some key differences on Sunspot in terms of performance. Okay, so the initial setup, if you want to run these examples on your own, you can download the code from GitHub here. And then you can get on a compute node and just determine, what's the number of ranks, how many nodes do I have. Ranks per node here is 1, but you can go up to 12 on Sunspot. The software setup that I use on Sunspot is with the preview module files and the latest frameworks drop. And then I have a virtual env here that I use to get some extra packages for Cosmic Tagger. And then the Python call looks kind of like this, and I'll walk through some of the changes that I make in the Python code in later slides. And then this is just for your copy paste benefit if you want to copy paste the code later. Okay, so on Sunspot, if you run Pytorch with Cosmic Tagger with synthetic data for a single GPU, the performance you get is this. So you can see, for example, the TF32 format, which is the default format, has pretty good performance out of the box, up to 32 images per second. FP16 is comparable to that, but not significantly faster or slower, whereas bfloat16 has up to a 25% performance boost for some mini batch sizes. So if you're going for reduced precision on Sunspot, and unless you have a compelling reason not to, you should, bfloat16 is almost always your best bet in terms of performance on Intel hardware. For some applications, you can unset this variable, which is set by default. So IPEX XPU 1DNN layout optimization. For Cosmic Tagger, doing unset for that yields a 5 to 10% performance improvement. You can compare the peak here is 44.3, the peak here is 45.9. Different apps show better performance with the variable set. So I recommend you try this. And I don't know what every application is going to get. It depends on the nitty-gritty details of 1DNN and whatever drop you're using. So it's worth trying. You may get a small performance benefit, but don't expect it to be life-changing. And just to show you some comparisons with A100. So this is with torch.compile on A100. which gives about a 2x speed up on A100 versus no torch.compile on PVC, since again, that's still experimental. So for a mini batch size of 1 with torch.compile, A100 is a bit faster than PVC. So 22.9 versus 16.3. But at a mini batch size of 8, they're comparable. So this is a single tile of PVC, by the way. So all the GPUs are 2 tiles. In general, applications that we're testing at Argonne, the performance of a single PVC tile is on average better than an A100. So when you bring your model to Aurora, you should expect to see per GPU about a 2x improvement in performance just from getting 2 tiles and each one being better. So certainly it's now the case that performance on the Intel GPUs for learning applications is quite good. If you want to scale up the model, it can be pretty easy if you're using something like DDP. So I changed an argument here, run.distribute equals true, which enables DDP in this code. And then you can launch with MPI as per usual. So you say the number of ranks and the number of ranks per node. Optimal performance is typically seen with 2 ranks per GPU, 1 per tile. So I set n ranks per node here, typically to 12. There are some configurations for small models that I won't get into today that get even better performance with oversubscribing the number of ranks per node, the number of ranks per tile up to 4. And then all reduces are done through the CPU sort of transparently. And that is still somewhat of an experimental feature for PVC, but you can get even better throughput scaling up that way. One thing about the GPU placement on Aurora, so sorry, this is a little cut off at the bottom. Similar to the variable CUDA visible devices, there's a variable for Intel that's called ZE_affinity_mask. And you usually set things to GPU.tile. So, your available GPUs are 0.0, you have 3.0, 5.1, etc. And you can set a string that is any combination and permutation of these. So you could reorder them by changing the orders here. You could use tile 0 exclusively by removing all the dot ones. We've done measurements. This was in March on Aurora with 768 GPUs. Tile 1 versus tile 2. Tile 1 is typically ever so slightly faster. Tile 0 is ever so slightly faster than tile 1. But it's a difference of, less than 0.5%. And the bigger difference you'll see when you really scale out is that there's a node to node and GPU to GPU variation that's up to 5% at the scale of hundreds of GPUs. So it's unlikely you'll ever see any performance difference between the tiles. More likely as you're scaling out and you're doing some sort of data parallel mode and you get locked down to the slowest tile, everything will just be locked to that rate and all the differences will wash out. There's also a detail on Aurora and the Aurora nodes and Sunspot nodes with CPU affinity. So running Cosmic Tagger with the configuration shown above, the local rank throughput I measured on the latest drop in the bfloat 16 version, so just trying to get the fastest performance possible. Without setting CPU binding, it was 37.3 images per second. And recall the single tile performance was about 45. If I set the CPU affinity to depth, you get about the same performance. When you set it to NUMA, it drops further. And if I set it to the dedicated settings from Intel, I got 35.7. And just to tell you what those are, it's this big, long, complicated list of CPU bindings. This is still definitely work in progress. So we're working on optimizing all of these settings. One of the tricky bits here is that there's 2 CPUs with 6 tiles each effectively and 4 NICs, network interconnects, and balancing each rank's CPU launching and GPU tile access and NIC usage is not so clear cut on Aurora as it is on a system like Polaris. So we recommend you try a couple of these. And as we get finer tuning of what settings to use, we'll update our documentation at ALCF for the users. There's also another quirk on both Sunspot and Aurora. When you scale out beyond 16 nodes, you have to set a couple environment variables. And this fixes some hangs and crashes due to communication message buffer sizes. There's really no detriment to setting these in your scripts below 16 nodes. I would like them to be set in the framework's module files by default, and that will likely happen sometime in the future. But for now, just make sure that these environment variables are in your scripts if you want to scale out beyond 16 nodes, or even just put them in all of your scripts. Okay, so I'm going to wrap up there for the talk about Sunspot and Aurora. We've got about 15 or 20 minutes left to field questions from anyone on any of these subjects. Thanks, everyone.
So can I ask a question?
Of course.
So the critical question here is there's a lot of Pytorch, for example, code that has specific, not just to CUDA device statements, but Pytorch statements that sort of have the CUDA keyword in them. And on AMD platforms, the way that this has been handled is it pretends to be a CUDA device, even though underneath it isn't. How is the transformation of the code handled, however, in the case of the XPU? Because it seems that it's quite different, and there is no such translation unless I've missed something.
You're correct. There's no such translation in the Pytorch user-facing code. So if you have code that calls torch.cuda or model.cuda, you will have to manually intervene and replace CUDA with .xpu, for example. Inside of the Pytorch code, things are more transparent to users. So if you've imported the Intel extension for Pytorch, operations that when you call convolution, for example, and the device, the tensor is on an XPU device, it will use the 1DNN operation instead of the cuDNN operation.
Right.
So mostly you have to do a find and replace of XPU to CUDA, or you have to do some sort of more complicated switching between the two.
Okay, so if I want to have a portable code, essentially, I mean, on the AMD side, I'm handled by the fact that unless I'm doing something very specific for looking for a specific NVIDIA GPU model, in which case it's going to give me nonsense. Code will just work, but to have a code that works for both XPU and CUDA devices, I'd have to put in if statements all over the place. And if I want to cover Habana devices as well, then I guess there's going to be even more if statements.
That's right. And I think a lot of people turn to frameworks such as PyTorch Lightning to help handle this because they have all the if statements for you.
Mm-hmm.
So that may be an option if you don't want to increase your
PyTorch
code
Lightning
length.
is an approach that would allow us to get over that. I see.
Yes, PyTorch Lightning has its own downsides in that sometimes you can't get at the features you want. But yes, and if you have any issues porting your code, feel free to open support tickets.
Is there a cheat sheet of the translation statements, or basically is it as simple as search and replace for .CUDA and replace it by .xpu?
I would say that it's just about as simple as you say, except for the memory layout point. And there's some performance tuning guidelines on the Intel extension documentation that you can reference, and they will have all of this listed as well. But in general, yeah, it's just about as simple as calling XPU instead of CUDA and making sure you get the the 1CCL bindings if you're using DDP.
Okay. All right. It'd be nice if you had something that could import and do this translation for free instead of having to do it any other way. I think that's what the Habana approach does. You import one package and it essentially translates the .CUDA statements to something else. So to the degree that there is any feedback that can be given back up, it would just make life a lot easier. Because I don't think people want to be maintaining two code versions. So anyway, thank you.
Yeah, sure. I will happily take that feedback to Intel as well. I saw some questions on the chat. Someone asked, is Cosmic Tagger the only comparison use case? No, definitely not. We collaborated with Intel for a publication last year at SC. It included Cosmic Tagger and several other applications, and we showed great performance across both Intel A100 and AMD devices. And we also track about 10 applications from our users over the course of the Aurora project that we've been using to measure performance for several years now. So we've seen performance comparisons go from 500 times slower than A100 to now, for some applications, 2 to 3x faster. Yes, I can share the link for that paper. I'll put it in the chat here in a minute. There's another question. Do you have a link that outlines how to apply for compute time on Aurora? How often are these calls? Quarterly, biannually, yearly? I will defer that question to Ray, since I have no role in the allocations program.
Okay,
Ray, you want to take that?
Yes. So if you just need so the large allocations are part of one of two programs, either Insight or ALCC, and those are granted once a year, but the two programs are staggered by 6 months. So the Insight the Insight applications are due somewhere around July 1st, and the ALCCs are due early in the year. So, although technically they can make exceptions to set them up at other times too. But anyway, you're probably really interested in a smaller project allocation, which is called a director's discretionary project. So you can apply at any time. There's no particular time for an allocation. So go to accounts.alcf.anl.gov, and you will see, if you go there, request allocation requests, and then it will guide you through applying for a discretionary account.
Thanks, Ray. I saw a couple more questions pop up while we were chatting about those ones. The supported version for JAX. Currently, the latest version of JAX is 0.4.25 on Sunspot. The development version of JAX from the JAX team, I think, is 0.4.28. So we're a couple minor versions behind the latest, but well ahead of 0.4.13. Are we planning to include Sunspot for upcoming ALCF trainings? I would expect that to be the case. I believe our next training session is likely in the fall. My guess is that will include Aurora, but a lot of that depends on what the status of the Aurora program is. So I can't make a prediction there, but there's certainly, if we're able to include Sunspot or Aurora, we will. Okay, I think I got through all the questions on the chat. Jump in on your mic or put more questions in the chat if you'd like to.
Hi, Corey. Great talk. I had if you could say a few quick words about the installation process, that'd be great. Just high level, what you had to do, standard things, some non-standard tweaks if you had to. That'd be great.
For the
Thank you.
Intel optimized software, it is not as straightforward as say for CUDA. You have to get basically, depending on the package you want, there are installation instructions for Pytorch, Tensorflow, JAX. We work closely with Intel on installing and deploying for Sunspot at the moment. I expect this to transition to an ALCF role once Aurora is in production, but right now Intel is installing the details of the frameworks, with the exception of JAX, which I'm building myself. So for details of the installation, I'd recommend you go on to the Intel websites and read their guides. I see another question, prior experience with diff racks on Aurora. I do not know in particular about diff racks. If it's a pure JAX code, it may work out of the box. If there's an application you want to try and see how it runs on Sunspot, and if it fails, please report back to us what fails and why, so we can take that to Intel. If it's something you need for your projects, we want to know. Okay, I see diff racks as pure JAX, so in principle it should work, but it may or may not have been fully validated. Will Pytorch also work since Pytorch does? Yes and maybe. So Pytorch, I believe is that geometric Pytorch and not the Gaussian processes version of Pytorch. In either case, some of them have extensions to Torch that have CUDA kernels. Okay, Gaussian processes. I believe we're looking at that, but I am not the expert on the Gaussian processes versions of Pytorch. Anything that's pure Pytorch should work functionally out of the box, and there may be performance optimizations needed. Anything that has dedicated CUDA kernels may require intervention to port some of those kernels to XPU. There's a question from Pablo. If you have your hand raised, feel free to unmute and just ask.
Hey, thank you for all the info. So I know this is about the ML frameworks, but I read that you have support for lamps right now in Aurora or Sunspot, I guess.
Mm-hmm.
And I do have a lamps extension for exporting the lamps information into arrays that can be read by JAX, for instance.
Mm-hmm.
And is there a way to get support to try to build this against the current lamp builder?
Okay, that's a multifaceted question. So
Yeah.
I'll try a couple answers and hopefully one sticks. I am not a lamps expert. We have them at Argonne and they are running them on Sunspot. So to get in touch with the experts who can help you build those extensions, we would need to sync, offline over, the ALCF Slack that has Sunspot support, or via a support ticket, or email me directly and I'll connect you. Assuming it can build, all of the frameworks that we've pushed Intel to support on Aurora are in principle meant to have the DLPack interface. So if your arrays from any package really can support the DLPack interface, you can.
Yeah, actually, that's what the library does. It kind of exports a DLPack.
Yeah.
Data structure that you can read from JAX, for instance, or Pytorch or whatever. But
wonderful. So it's in principle supported, and even at 0 copy on the GPU. Yeah. That said, the matrix of support, framework A to framework B via DLPack is massive, and not everything is possible to test even. So I would be really interested to hear, does it work or does it not work? And if it doesn't work, we can actually, we take bugs to Intel for things that are broken and use them to validate later releases. So failing code that should work is one of the most valuable things you can send to us.
Okay. So then I'll reach out to try to see if we can do something about this. Thank you.
Terrific. Okay, thanks everyone. If there's no more questions, I think we're done for today. You're always welcome to follow up with ALCF via support.